Okay, good morning. So, I realized there is one page left in the book that I haven't talked about that, so this lesson probably will be a little bit short. I will finalize this. It is called modular equations, or probably it's better to write congruence equations. That is a very simple lesson, and then from next session we will start the next section. But number theory in principle will be finished here, okay? So the motivation is this. So for example, do you remember we had an equation in Math 1C even. I give you 2x equals to 3, and then you want to solve this equation. Yes? So then you don't have any problems. If you want to solve that, you divide both sides by 2, and then you get 3 over 2. Yes? So that is the answer that you get, as simple as that. But of course, when we talk in number theory, we are actually interested in integer answers, not something like that. Yes. So similar to this, we can have an equation of this form. Instead of having equality sign, I can have congruency, and then I can choose a modulus, for example, 5. Yes. So this means that I am looking for all integer values. This is important. This is the difference between this normal equation. So here I have one equation, I have equality sign, which is a strict relation between numbers, and this is the only solution, which of course is not an integer, yes. But now I can ask a similar question, that what is the integer value for x, if there is any, so that the left-hand side becomes congruent to 3 modulo 5. Yes, so that is called a congruence equation. So we want to be able to solve that. I don't know why the book has talked about this. The way that they have described it here is not complete. And I would prefer not to talk about this, but I will keep it exactly at the level of the book. So the question is that A and B here is these numbers 2 and 3 are given to you. Here I could have given you non-integer numbers, but here I have to give you integer numbers. Here you could find a number which is not an integer and it is still acceptable, but here you are only looking for integer values. Yes. So it means that can we find x so that x is an integer or not? That is actually the question. But of course, I can write the same equation, more or less. I can change the module, yes? I can solve the same equation in 7. Of course, the answer that satisfies this equation is not necessarily the one that satisfies this equation as well. So even if I keep the left-hand side and the right-hand side, I can still change this module to different numbers and still solve the problem. Yes? So that is more or less the question. So we have A and B are integers. M is a natural number greater than or equal to 2. And then Ax is congruent to B modulo M is called a congruence equation. Yes, and the goal is to find, we can talk about all solutions, but according to the book you only need to find one solution, so we will not go through those things, okay? So the point is that can I find a value for x, a particular, not all of them, a particular solution, so that x belongs to z. Yes, we want to answer this question. To understand this problem, I need to remind you a little bit about what we learned. Probably you know about it, and that is the great common divisor, the greatest common divisor. or GCD for short, okay? So what is the greatest common divisor of two integers? For example, I give you 18 and I give you say 24, and I ask you to find the greatest common divisor of these two numbers. What is the meaning of that? Let me just solve this simple problem using exactly the words that I am using. I want to find the common divisor. So it means that I need to look at all the divisors, positive divisors of 18. So what are the divisors of 18? I don't know, let us invent a symbol for that. The set of divisors of 18. This is not a standard symbol, I'm just using it. I am telling you that D of 18, I mean the set containing all positive divisors of 18. So what is that set? So what is the first element here? Do you know the divisor? Yes, the divisor means a number that these two numbers are divisible by that. For example, 2 is a divisor, yes? Because 18 is a divisor for 18. 3 is a divisor for 18. I don't know. 18 is a divisor for 18, but 18 is not a divisor for 24. Yes, 12 is a divisor for 24, but not a divisor for 18. Okay, I want to write all the divisors by 18, positive divisors, because we can also have negative divisors. So what is the first element here? 1. The first element is 1. Yes? What is the second element? 2. The third one is 3. The next one is 6 and 9, and finally 18. Yes. So this is the set of all positive divisors that you can imagine for 18. Let us do the same thing for 24. So what is that? D of 24. I told you that this is not a universally adopted symbol, but I'm just using it. So I'm saying that D of 24 means the set of all positive divisors of 24. So again, what is the first element? 1, and then you have 2, then you have 3, 4, 6, 8, 12, and finally 24. So these are the all possible divisors for 24. And now let us look at the word common. So we check the word divisor. This is the set of divisors for 18, the set of divisors for 24. What is the meaning of the word common? In the set theory language, it means that what I am interested in the intersection between these two. Yes? Yes. That's the intersection between them. So if I find the intersection, what is that? 1, 2, 3, and then finally 6. So if I ask you what is the name of this in English, you would say that this is the set of common divisors. And then finally the word greatest. So what is the greatest common divisor is 6, yes? So it is clear that this question mark is 6 here. Yes, is that clear? That's the meaning of the greatest common divisor. Of course, there is also another way to find this, especially if the numbers are big. Do you know that? How we are supposed to find the greatest common divisor? Using factorizing the numbers to the prime numbers, yes? So you know that every number can be written as a product of prime numbers. If you write it in that way, that is called factorizing the number, yes? So I don't know which method you are familiar with, but what I do, I write, for example, 18 on the left-hand side of a vertical line, and I will put the prime numbers here so that 18 is divisible by that. So I don't know which one you want to choose, but probably the simplest prime number is 2, yes? 18 is divisible by 2. It's important that 2 should be prime. And then you do the division. What happens? It becomes 9. And then you divide it by, you cannot divide it by 2 anymore, so you can divide it by 3, and then it becomes 3, and then you divide it another times by 3, and it becomes 1. And mathematicians have proven that this is guaranteed that you will always end up with 1. That's always guaranteed that if you, for any number, if you start doing this process, it becomes at a stage that you end up with 1. And when you end up with 1, the process is finalized and finished. And what you can do, you can write 18 is equal this number multiplied by that number multiplied by that number. But then, because 3 is repeated 2 times, so it becomes 3 to the power of 2. So this is called factoring 18 to prime numbers. Yes? And it is shown by mathematicians actually that this factorization, except the order of the factors, is unique. So for example, one of you might get this, one of you might get this, etc., etc. But you cannot find a completely different factorization. So factorizations up to these factors, the order of the factors is unique. And this is, by the way, the reason if someone asks you what is 1, 1 is a prime number or not, what's the answer? You remember what's the meaning of the prime number? Yeah. A prime number is a number which is divisible only by itself and 1. So why we don't, so if someone asks you 1, is 1 a prime number or not? What's the answer? Because 1 has also the property. It is only divisible by itself and 1, yes? Yes. So can we call 1 a prime number? It's a convention, no. 1 is not a prime number. So remember, by definition, 1 is excluded from the set of prime numbers. So the smallest prime number is not 1. The smallest prime number is 2. And 2 is the only even prime number, yes? Other prime numbers definitely should be odd. By why they have, mathematicians have this convention, because if you do not have this convention, then you lose the uniqueness part of the theorem. Because you can write this and call it a factorization of 18. Your friend can write this, and of course another friend can write this, yes? If I consider 1 to be a prime number, this product is 18, and it's a product of prime numbers if 1 is supposed to be a prime number. And then another person can write it 3 times 2 times 3 times 1, and then another one here. So you see, this one is also a factorization to prime numbers if I accept that 1 is a prime number, yes? Because this product is 18 and all the factors are prime numbers. So if you insist to keep 1 to be a prime number, you will lose this uniqueness there, yes? But uniqueness is more important, so mathematicians actually see that it's better to exclude this from the set of prime numbers. If a number is not a prime number, what is it called? It's called a composite number. Yes? But 1 is not composite, yes? Because it actually satisfies the properties of a prime number. It has been excluded from set of prime numbers because of convention. So if a number, so 1 is neither a prime number nor a composite number, remember that? But if a number is not composite and it is not equal to 1, then it is prime. Or if a number is not 1 and not prime, it's called composite number. Yes? These are the terminologies, good to know. Okay, and then you do the same thing for 24. So 24, you do, for example, you divide by 2, it becomes 12. You divide again by 2, it becomes 6. You divide by 2, it becomes 3. And then you have to divide by 3, and then you see that you end up with 1 again. And then what is 24 then? 24 is 2 times 2 times 2, which is 2 to the power of 3 times another 1. It's this one. Yes? But now, using this, can you cook up a recipe for me so that how can, after factorization, how can I find the greatest common divisor by looking at the factorized form of my numbers? Yes? So I want to find the greatest common divisor of 18 and 24. I did it before, just using the words. Of course, this method is not very, if the numbers are big, this list actually is very big, yes? But here it's more efficient to do this. Okay, so how should I write this? So I want a number so that 18 and 24 are divisible by. So let us write as a fraction. So you want to write a number in the denominator for this and that, so that when you do this division, it becomes an integer, because I want to have 18 divisible by that number. I want to have 24 divisible by that number as well, because I want to have this integer. Okay, so then can you tell me, and then I want to have the question mark the highest value. So it is clear, what should I do? So in this number, question mark, can this number contain a factor other than 2 or 3? No, because if I have a factor other than 2 or 3 here, then definitely 18 is not divisible by that, because the only factors in 18 are 2 and 3. The only factors in 24 are 2 and 3. So definitely the question mark cannot contain a factor other than 2 or 3. So, but is it guaranteed that this is the highest one? So for example, can I make these to appear more than once? More than once for 24 is okay, because 24 contains 3 factors of 2. But 18 only contains one factor of 2. So I cannot raise the power of 2 more than 1, yes? Otherwise, that's 18 will not be divisible by that. Can I increase the power of 3? No, because even though I can still increase the power of 3 to 2, 18 contains 2 factors, but 24 only contains 1 factor. So this is the only one. And what is the answer? The answer is 6. And that 6 is exactly the one that we got here. Yes? So if I want to cook up a recipe, you can factorize numbers, and then you can choose the common factors that appear with the lowest power. Yes? Is that clear? So you factorize the prime numbers, you choose the common factors after factorizing them, and then you choose the lowest power for each factor that appears in the factorization. Yes? So here I have 2 and 3, I have 2 and 3, so the common factors are 2 and 3. The lowest power, the lowest exponent for 2, here this is 3, here is 1. I choose the lowest one, which is 1. And here the power is 1, the power is 2, so the lowest one is again 1. So that is the idea of how to do it. Yes? Another way to do this, which is relevant to what we want to discuss today, is what is called the Euclidean algorithm. So if someone asks you what is the purpose of Euclidean algorithm, you will tell that Euclidean algorithm is an algorithmic way to calculate the greatest common divisors of 2 integers. Okay, but this is a theorem, of course. You have to, if you want to understand it a deeper way, you need to know the proof. But I just want to follow the book. Okay, so what is the idea? What we can do here is this. You have 24, so we want to do the same thing. I will describe it by example. So 24. Okay, so you want to find this. According to Euclidean algorithm, you divide, for example, the bigger number by the smaller number, and then it becomes 18. So what is the quotient here? The quotient here is 1. What will be the remainder? The remainder is 6. Yes. So you take the bigger number and then divide it by a smaller number, and then you find the quotient and the remainder. And every time, do you remember, if I have this, let me recall you the names. This one was the dividend, and this one is called the divisor. Yes. And of course, you know that this one is the quotient and this one is the remainder. Okay, it's a little bit bad name. You see the name divisor here is the same divisor here that I'm using, but they are different things, yes? Okay, so, and then what you do, you take the divisor and then divide it by the remainder, and then you continue this process. Okay, so you take the bigger number and then divide it by a small number. You find the quotient and you find the remainder. Every time you have to pick up the divisor and the remainder and do the division once more. According to this Euclidean algorithm, you will definitely reach to the remainder 0. This is guaranteed by the theorem that we want to skip. But if you follow this process, I will take 18 And I divide it by 6. What is the quotient? 3. What is the remainder? 0. So this was very simple. Okay? So this Euclidean algorithm guarantees that if you follow this process, you will definitely end up with 0. And of course it is clear somehow, because every time that you divide, this remainder should be smaller than this number according to the division algorithm, yes? And then this remainder should be smaller than this one. The next remainder should be smaller than this one. So eventually it will reach to 0 somewhere. So this is an intuitive way of understanding it. So when you reach to 0, the previous remainder is what you are looking for. Yes? So here, by just doing simple calculation like this, you can see that the greatest common divisor of 24 and 18 is actually 6. For example, let me give you another example. So let us find the greatest common divisor of, I don't know, 84 and 60. Of course, this is something very simple. You can just use that method if that's easier for you. But there is a reason that in this discussion of congruence equations, this way of finding the greatest common divisor is more important than the other ones. I will come to that shortly. But let us just use the Euclidean algorithm to find this once more. So what I'm supposed to do, I will take the bigger number and I divide it by the smaller number. So what's the quotient here? What's the quotient? 1. And what's the remainder? 24. And then what I'm supposed to do, I will repeat this process by these new numbers. So I will take 60 and this time I will divide it by 24. So what is the quotient here now? 2, and the remainder is 12. And then I repeat this process between these two numbers again. So 24, it becomes 12. What is the quotient here? 2, and what is the remainder? 0. As soon as I get 0, the previous remainder is my answer. So the answer to this is 12. Okay, so let us check this one using that method as well. So for example, if I want to use this method, the previous method, I divide by 2, it becomes 42. I divide by 2, it becomes 21. I divide by 3, it becomes 7. I divide by 7, it becomes 1. So if I ask you factorize 84, so this is not useful for factorizing 84, yes? But here I'm factorizing it. 2 appears 2 times, multiplied by 3, multiplied by 7. And then if I go to 60, I divide it by 2, it becomes 30. I divide by 2, 15. I divide by 3, 5. I divide by 5, 1. So you see here, my goal is to end up with 1. But here, that's actually the quotient. But here I want to end up with 0 for the remainder. So then if I write 60, it becomes 2 to the power of 2 times 3 times 5. Okay, now if I ask you, do you remember the recipe? If I ask you what is the greatest common divisor between 84 and 60, I need to find the common factors. 2 appears here and there, so that's a common factor. 3 appears here and there, so it's a common factor. But 5 is here but not there, so it's not a common factor. 7 is there but not here, so it's not a common factor. So these are the only common factors that I have. Yes? But I need to find the lowest exponent for that. So what is the exponent of 2 here is 2. What's the exponent of 2 here is also 2. So what is the lowest exponent is 2. What is the exponent of 3 here is 1. The exponent of 3 here is 1. So what is the lowest exponent is 1. And if you calculate that, what is the answer? Is 12. And 12 is the answer that we got from that. Yes? Is that clear?
Yes.
So, but here we want to emphasize on this method. And the reason is that there is a theorem, I just mentioned the name, it is not probably mentioned in the book. So this is called Bezel, I think, the pronunciation, theorem. So this is not in the book, but I think they are using it without mentioning the name. So what is the content of this theorem? It tells you that if I have A and B integers non-zero, and if GCD, the greatest common divisor of A and B, let me call it D, this claims that then there exists an x and y in the set of integers so that ax plus by is equal to d. So that is the content of the Bezel theorem. So it tells you that if you have two integers and if you find the greatest common divisor of those two integers, if you want to, this person guarantees that you can always find x and y integers so that this this ax plus by is equal to d. So you can write the greatest common divisor in terms of the numbers a and b themselves. Yes, and of course it is not unique. X and y could be different numbers. Okay, for example, if I ask you, can you find 1x and 1y for 84 so let me write for 18 and 24 first. So here we realize, so this is something, the proof of this is a little bit difficult, but it is not also in the book, but it's good to know the name. Let me start from here, GCD of 18 and 24. What was that number? It was 6. Do you remember? We calculated that it is 6. Now, my question is that, can you find these claim numbers for this case? What does it mean? It means that, can you tell me an x, can you tell me a y from the set of integers so that 18, the first number multiplied by x, plus the second number multiplied by y becomes 6? Yes? Of course, if the numbers are small, might be you were able to guess, yes? But the point is that if these numbers, if you want a systematic way of finding x and y, you have to use Euclidean algorithm. Okay? So I don't know, can you guess these numbers? Here the guess is very, very simple, isn't it? So can you guess integers x and y so that this holds?
Minus
1, yes. Which one? This one 1.
Yes,
This one minus 1, yes? So minus 18 plus 24 is exactly 6. So here you really don't need to do anything systematically because the problem is so simple that you can guess. So here, for example, x is equal to minus 1, y is equal to 1. I don't know, can you guess another numbers? For example, I can guess x equals to 3, so it becomes, and then y minus 2. Do you think it works? 3 times 18 is 54, and 2 times 24 is minus 48, and if you subtract them, it becomes again 6. So you see, at least we have one set here, one set there. So no, there is no way that x and y are unique, but this theorem only claims that there are integers x and y with that property. Yes? And then the point is to find these numbers, one pair of these numbers. Of course, you can talk about all possible pairs, but this is not included in the book, and I really don't want to go through it. Okay, so we want to find, in a way, systematically, to find x and y. And this is the idea that we come from here. So you see, you can rearrange this Euclidean algorithm to find that answer immediately. How? When you found your GCD using Euclidean algorithm, here in this line, what you can do, you can take this one and move it to the left. So what happens? This becomes 24 minus 18 times 1 is equal to 6. Yes? And then just immediately compare this with what you are going to guess. Yes? So you see that 24 is multiplied by 1 actually, even though it is not written. And this is minus 18. I want to have positive 18. So the price that I have to pay is to write 24 times 1 plus 18 times minus 1. My goal is to make positive 24 and positive 18 apparent in my equation. And then I compare this with what I need. And then comparing these two, I can immediately guess x and y. X is the coefficient of 18, which is minus 1. And y is the coefficient of 24, which is 1. So we were able to guess this solution. Yes? Is that clear? But this is just one particular solution. And I told you that I don't want to go deeper into that because we will not be able to finish other parts. But let me do the same thing here. This would be a little bit harder. So let me do the same thing for 84 and 24. So let me ask you this question. So let me keep this one. And then let me clean this. What Bezel Theorem claims is that we realized here, if I ask you what is GCD of 84 and 60, according to this calculation is 12. Okay? Now, Bezel claims that you can find integers x and y, integers, yes, such that 84 multiplied by x plus 60 multiplied by y is equal to 12. You want to find them. Yes? Okay, how can I find them? You see that if the numbers are bigger, then the guessing is harder. But of course, you really don't need to work with bigger numbers. Yes, you can divide everything by, I don't know, for example, 4 and make it simpler to guess. Okay? But let us not to do that. Let us follow this algorithm. Okay, so how can I do that? You will start with the final answer 12. So this you need to learn. From this equation, so you find 12. How? I keep 60. So be careful, you are not calculating anything. You want to rearrange these terms in a way that you can compare your final answer with this one and be able to guess the particular solutions. So what I do, I will keep 12 here and I move this to the left. So it becomes minus 24 times 2. Yes, this is understandable. Of course, this is not a big deal. Yes, 24 times 2 is 48. 60 minus 48 is 12. Yes? But if I ask you, is this a good thing to have? I would say no, because I want to see 84 in my equation. I want to see 60 in my equation. Of course, I have 60 here, but I do not have 80 yet. So what I need to do, I need to go to the previous step and find 24. Okay? So how? So you continue, you write 60. Every calculation should be formal. You are not allowed to calculate something because calculation is simple. The goal is different. So here minus, you have a 2 here. But you go to the previous step and find 24 from this equation by moving this term to the left. So it becomes 84 minus 60 times 1. Yes? And then what is the goal? The goal is to have a combination of 84 and 60. I achieved the goal. This is a combination of 84 and 60, but I have to rearrange them in a way that guessing x and y becomes easy. Yes? How can I do that? So this becomes 60. I multiply 2 here. Do not multiply by that because I want to keep 84 in front of my eyes. I have a negative sign. So it becomes minus 84 times 2. And then if I multiply this minus, it becomes positive. I multiply 2, do not multiply it by 60 because you want to keep 60, so it becomes 60, you multiply 2 here, it becomes 2. Yes? And then you simplify. I have one 60 here, I have 2 more 60s here. So how many 60s do I have? I have 60 times 3. Yes? And this minus 84, I want to have it positive 84, so I will make it positive 84. Instead of putting the negative sign here, I put the negative sign there. Yes? So the point, I don't know how to teach it, but the goal is to have this combination. And the rule is that you start from the last one, move this to the left, and then find this one from the previous one and do it once more. You know, this might be a little bit messy, but this always works. And then if you have this one, now guessing x and y are very easy now. Because 12 is equal to this expression. And if you compare it with that one, what is the value for y? The value for y is 3. The value of x is minus 2. So this will definitely give you one possible value for x and y. Yeah, is that clear? Yes.
Can you explain again the first step where you...
Here?
Yes, how did you get... where is the 84 there?
So you here, 84, where is coming? So no, I told you that. Whenever the point of this question is that we find the divisor, the common divisor. According to the Bezel Theorem, we should be able to find x and y so that 84 multiplied by x plus 60 multiplied by y becomes 12.
Yeah, but then you wrote 12 is equal to 60 minus 24 times 2.
Yes, it's coming from here. So I move this one to the left.
Okay.
Yes, so these equations are valid.
Yeah.
So this means that if 60 is equal to this plus 12, it means that when I moved it to the left, 60 minus this number becomes 12.
Okay. I thought
Yes?
you had to keep 84 there as well.
Yes, no, but let me just go step by step. So now if I ask you what the combination is, this is a combination of 60 and 24. But what I need a combination of 60 and 84. Yes? So this means that I will not touch 60 because I need it, but I do not need 24. I need to get rid of 24. So this is going to the previous step. And 24 is this number minus that number. So instead of this one, I copied and pasted. Instead of 24, I wrote this from this equation. And then I multiplied by 2. But then you need to understand, you are not allowed to multiply this. So that's not according to your goal. If you multiply 2 by 84, then it becomes, of course, it becomes, I don't know, 168. But that is not, there is no point to do that because I want to keep 84. And then you simplify and then you compare, then you find the answers. Is that clear? Yes? Okay, now why this is relevant to the starting question, and that would be the final problem today. So what is the relation between these kind of things, okay? For example, let me choose a problem, one of the problems in the book. So for example, you're supposed to solve this equation. It is in the book. You want to solve 15x congruent to 9 modulo 3. Now the point, we come back, we want to find one x, not all the x's. Yes? Do you remember there were two operations that we didn't have them for congruency even though we had them for equality? What was those relation?
Division.
Division and taking the nth root. So that is why solving this equation is easy because you divide. But solving that equation is not that trivial as this one because you are not allowed to divide by 15. Yes? So you need to find an integer value, if any, that satisfies this equation. So how we do that? So you need to know how to interpret this. You would say that 15x congruent to 9 is equivalent. Do you remember? it is equivalent to saying that 15x minus 9 is divisible by 3. That's the meaning, yes? And what is the meaning of divisibility? It means that there exists, usually I write q, but let me change my letter to y here. There exists a y in z such that 15x minus 9 is 3y. Is that understandable? So I gave you a congruence equation. You are supposed to find one integer x, not all of them, just one that satisfies this equation systematically, not based on your guess. Yes? Because by guess x is equal to 2, yes, isn't it? Because 2 times 15 is 30, and then if you subtract 9 from it, it becomes 21, and 21 is divisible by 3, so I just got my answer. Okay? The point is that to learn this systematically. So, this is the meaning of the congruency. When we say that two numbers are congruent in some module, it means that the left-hand side minus the right-hand side is divisible by the module. And when a number is divisible by another number, it means that there exists a y, an integer. Usually at this stage I write q. Okay, but let me change the letter to y here, you will see. Such that this, and then what happens here, I move this to the left and 9 to the right. Oh, sorry, this was completely the other way around. Anyway, this is why I was saying that it doesn't mean that we cannot solve it, but okay, let us solve this one. The one in the book is different. The one in the book, the module is 9. This number is 3. Okay. So here, if you want to solve this problem, you take this number and that number with the positive sign. Okay, in the negative sign you can absorb them in the quotient here. So you find GCD of 15 and 3. Okay, these numbers are so small that it's very easy to do them, but let us just do them. That was actually very tricky. So here 15, you divide it by 3. What is the quotient?
5.
5. And what is the remainder? 0. Actually, there is no previous remainder to it. So what is the greatest common divisor here?
3?
No, 3. When there is nothing before that, it means that, so you see, when you divide 15 by 3 and the answer becomes 0, so it means that this number itself is the greatest common divisor. Yes? So this means that the greatest common divisor, so that was a very, very bad example. Sorry. It is equal to 3. Okay, can you guess that? What is that? How can I write this? How can I write 3 in terms of that? Because there is nothing that you can solve from it. So how can I write this? 3 is, can you tell me? Because this is a trivial case. I want to write 3 as a combination of 3 and 15. So what should I do? 15 times the most trivial one. 15 times, 3 times. Yes?
0 and 1.
0 and 1. Yeah, so this is not a good question actually. So that is very simple. Yes. But the point is that here I have a 9, not 3. What I'm supposed to do, I need to make 9. So I multiply everything by 3. I multiply this by 3, it becomes 9. I am not allowed to multiply this by 3 because I want to keep 15. I multiply 3 in 0, but of course this becomes 0 again.
Yeah.
And then I will have to multiply here by 3. If I multiply this by 3, it becomes 9. I don't need 9. I want to keep 3, so I multiply here. So what is happening here? It becomes 3 times 3. But then I need to fine-tune this signs. So the sign here is not okay. So this is very minor adjustment, yes. So what can I write? I can change it to negative. I keep it 3, but I am supposed to do it what? Negative 3. And now if you compare this one with that one, your x is found, yes? So x is 0. The one that I guessed was also correct, but it was not this answer. But that one answer is enough, yes? So this answer is 0. Is that clear? So now let me solve the problem in the book. Let me interchange these two. So 15x is congruent to 3 modulo 9. We want to solve this one. But again, for example, do you agree that 2 is again the answer here? Yes? Because this time 2 times 15 is 30. 30 minus 3 is 27. 27 is divisible by 9. But if you just answer 2 in the exam, that would not be accepted. So you need to do it systematically. Okay? So how should we do it systematically? What I will do, I will write this, I would write 15x is congruent to 3 modulo 9. This is equivalent to saying that 9 divides 15x minus 3. This means that there exists a y in z such that 15x minus 3 is 9y. Then I move 9 to the left and 3 to the right. I will get this, yes? And then what I'm supposed to do, I take the positive number 15 and the positive number 9 and find the GCD, not using the factorization method, using the Euclidean algorithm method. So you want to find that. What I'm supposed to do, I take 15, I divide it by 9 in my head. What is the quotient? 1 times. What is the remainder? 6. What I'm supposed to do, I will take 9, I will divide it by 6. What is the quotient? 1. What is the remainder? 3. I have to repeat the process. 6, take it 6, and then divide it by 3. The quotient is 2, the remainder is 0. When you reach to 0, then the previous one is your greatest common divisor. So the greatest common divisor would be here. Yes. But now your point is to find one possible answer systematically. So how am I supposed to do? I need to write 3. I'm supposed to write 3 as a combination of 15 and 9. Okay, so I start from the last one. So here 3 is equal to 9 minus 6 times 1. And then this, if I ask you what is this, it's a combination of 9 and 6. But I want to have a combination of 9 and 15. So it means that 9 is something that I want, I keep it, but I want to get rid of 6. So I go to the previous step and find 6 here. So what is the answer? I copy and paste 9 minus, open a pair of brackets, I have this dot 1 here. Instead of 6, I use this equation. So it is 15 minus 9 times 1. Yes? And then you multiply inside. So it becomes 9 minus 15 times 1 plus 9 times 1. You have 1 9 here, you have another 9 here. So how many 9s you have? You have 2 9s. So it becomes 9 times 2 minus 15 times 1. And if you go back and look here, you need to fine-tune the signs in a way that it matches with this one. So what should I do? Instead of minus 15, I need positive 15. So I would write it positive 15, but I will get a minus sign to this one. Yes? And then I want to have a negative 9, but I have a positive 9. So I write it negative 9, but I cannot change it unless I put a negative 1 there as well. Yes? And then now it is very easy to compare this one. You see, what I get is that 3 is equal to this. Of course, this is a very simple thing, yes? Minus 15, positive 18 is exactly 3. Yes? But we did it systematically. So then it means that if I compare this 1 with the equation that I'm supposed to find. What is x here? X is equal to minus 1. Is this the only solution? No. This is one answer, and that is called a particular solution. And according to the book, you need only to find this particular solution. Okay, so let me give you this. What do you think about this equation? If I just have this equation for you, but instead of 3 on the so let me just write this for you, and then put 1 here. Yes?
I'm sorry. My question wasn't about that.
Okay.
But the part where you find the greatest common
Divisor.
yeah, isn't that guaranteed by the theorem?
Yes.
So when you get 3 up there, do you have to do the algorithm, or can you?
No, the point now. So might be the logic is a little bit convoluted. Okay. So what is your question? Your question is fine.
When you have 15x minus 9y
Yes.
equals to 3,
Yes.
can't you immediately conclude that 3 is the greatest common divisor without doing the next step?
No. Because, for example, they could have asked exactly like here. For example, if what happened if this is 6? If this is 6, 6 will appear here.
Yeah.
But this 6 is not. So So you see. So this 9 appears here, this 15 appears here, this number appears on the right. So assume that I give you the same question, keeping this one the same, but I change 3 to 6. Okay? Then you will write the same thing, but on the right you will get 6, but the greatest common divisor is still 3, not 6. Is that understandable?
Yeah.
Yeah. Okay, so what do you think about this equation then? 15x, we want to find, if possible, that x, in a way that 15 times x is congruent to 1 modulo 9. I don't know, they have talked about this in the book, but for example, if you want to solve this, let us just do it as before. If you want to do it, you would say that this is equivalent to saying that 15x minus 1 is divisible by 9. This means that there exists what? Y in Z such that 15x minus 1 is equal to 9y. And then I move this to the left exactly as before, yes? Okay? Okay, then what happens? Everything that you need is on the board. You take 15, you take 9, and you find the greatest common divisor as before, so I don't repeat that. The greatest common divisor is that. And then what you do is this process. Yes? So what happens then? Then 3 becomes equal to that. So this is what you can get. Okay? But this is not good enough because I want to compare it with 1. So if I compare it with 1, then what should I do? Is that clear? So if I change the number from 3 to 1, everything remains the same. Instead of 3, I will have 1. But finding the greatest common divisor between 15 and 9 is the same process. And writing the greatest common divisor as a combination of 15 and 9 is the same process. So I will get 3 is equal to this combination. But I want to compare this equation with that equation in order to be able to guess these two numbers. Okay? But that is not exactly what I want. I have the nice combination here, but instead of 1, I have 3. So what I'm supposed to do if I want to compare? I want to make it 1.
Yes.
But then when I divide it by 3, what will happen? So this becomes 1. If I divide 15 by 3, then I will lose my guessing method, yes? So I have to divide this by 3. So it becomes 15 minus 1 over 3 and then minus 9 minus 2 over 3, yes? But can I say that the x is minus a third? No, because I'm looking for the integer value. So then what is the conclusion? There is no. Why? But this is very evident from the beginning. You really don't need to, so this is not mentioned in the book. In principle, when you want to start solving a congruency equation, it is better to have a guarantee that is there a solution or not. Because if you have a simple criterion so that this is not possible to solve, you just don't leave it and don't solve it. Exactly like, I don't know, a quadratic equation. You calculate delta. If delta is negative, you'd say that there is no solutions. Yes? So something like this is also happening here. So could you see in the beginning, there is no hope to continue. So if I solve this and write to this, I will leave it and I understand there is no hope to continue. Why there are no x or y so that this is valid? Is it possible, without calculations at all, is it possible to find x and y in a way, integers, so that the left-hand side becomes 1? The answer is no, but do you see why? It's a very, very simple argument that tells you that don't continue. You will not ever find x or y integers. Very simple argument. So here, can I factor 3 out or not? This becomes 5x minus 3y is equal to 1. Now can you see the point? Yeah, so here, x and y are supposed to be integers. So this combination is an integer, so let me call it q. So the left-hand side is a multiple of 3, the right-hand side is 1, but 1 is not a multiple of 3, yes? So it means that when you reach to this point, you should understand that there is no hope for continuing this. Yes? Is that clear? Okay, and if I want to give you that, it's not in the book, but the theorem is that if you have this equation, okay, if you find the greatest common divisor, so these numbers, you see, be careful. This 15 is the same 15 here. This 9 is the module. Okay? So here, so we are always calculating the greatest common divisor between this coefficient and the module. Yes? So the greatest common divisor of this coefficient and the module, if this does not divide B, then there are no solutions. So let me just write it properly here for you. So AX congruent to B modulo M has a solution. By a solution I mean integer solution, if and only if the greatest common divisor between A and M divides B. Yes? So I don't know why they have talked about this in a very short way. So these are deep things if you want to go through them. So for example, if you give me this, I will not continue solving it. Yes, because in my head I calculate the greatest common divisor between 15 and 9. What is that? It is 3. And I ask myself, is 1 divisible by 3? No, so there are no solutions. But in the previous case, what is the greatest common divisor between 15 and 9? Is 3. But this 3 is divisible by 3, so there are solutions. In that case, it is 3, 9 is divisible by 3, so there are solutions. So, yeah, if you use it, I accept it because it's better to know that. So, AX plus B has a solution if and only if you calculate the greatest common divisor between these two numbers, it divides the third number. If this is the case, then you will be able to find solutions. And by the way, know about this, you will get infinitely many solutions. Okay, not just one.
But this is not in the book, so let us not continue with that. By the way, there is a name here I see now. So let me just tell you the name as well. So these equations in number theory are ubiquitous. So you have one equations, but you have a number of equations, but the number of unknowns is more.
Yes.
Okay? These kinds of equations that you have the number of unknowns more than the number of equations are called Diophantine equations. This is a Greek mathematician, Diophantus or something, but this is Diophantine equations. So I saw the name there now. So Diophantine equations in number theory are equations in which the number of equations is less than the number of unknowns. Yes? And then you want to solve. But that is also good to know about this name. Okay, there are so that is just half a page in the book. So we are done. Even though the name of the chapter is number theory, but the next one is number sequences, which is not related to number theory at all. Okay, and now we can go much faster on that because that is easy. But then there is a very, very important part which will be left, and that is mathematical induction. I want to spend quite some time on it because that's very important. Okay, I will stop the lesson today here. I will try to update the Google Classroom so that if you want to work on the problems, you can start. Do you have any questions? Yes? Okay, thank you.
So,